Digital twins are the heart of the fourth industrial revolution. With rapidly evolving technologies like machine-to-machine communication and the rise of ever more intelligent automation, the basis is set for powerful virtual representations of real-life objects. And this leads me to our next talk and our next guest. Christian Stapel, Partner Data and Technology at MHP Management and IT Consulting, will present a vision of digital twins in intelligent automation, which goes far beyond the collection of data on a specific real-life object. I'm looking forward to your presentation, Christian.
Thank you very much for the nice introduction. So, now should work.
Yes, we can see your screen.
Great. Yeah, thank you for having me here. And welcome to all viewers who are interested in digital twins, artificial intelligence, and how this could push boundaries in intelligent automation. My name is Christian Stapel. I'm partner of the consulting services, data and technology at MHP. Let's go right into it. Technology disruption within the mobility and manufacturing industry is already shaking our established enterprises. Entire ecosystems, like the automotive industry, are facing a multiple disruptive technology change. The cars are getting electrified, smarter, more intelligent, and even autonomous. Similar changes are happening to the production. The machinery gets its own artificial intelligence, acts autonomously, and the robots are even interacting within the worker side by side. There's almost no area that is not affected. The logistics is changing to smart logistics. Whole cities are becoming smart cities. With a widespread usage of autonomous acting systems, there will new challenges occur. But what are these challenges? In many cases, it is a process optimization issue. Process optimization of highly integrated and autonomous acting systems are facing the challenge of a local maximum output versus a global optimization maxima. One example. A single autonomous robot will try to achieve his local maximum output. He will just try every time again. But the company has an interest in a global optimization maxima for the whole factory. Second, operation in integrated environments. An autonomous factory needs maintenance prediction or another intelligent surveillance because there is no machine operator any longer who can act and react on stray noises or on loose cables and fix the issues before bigger damage happens to the shop floor. Third, stability and risk assessment for smart and self-operating systems. Let's stick to our shop floor example. How can a fleet of autonomous acting industrial trucks act efficient and robust at the same time, be resilient to any last-minute changes in the production or on the supply chain? Fourth, ethical considerations of decision-making systems. This challenge describes a lack of explainability when it comes to higher integrated artificial intelligence-based systems that led to poor opportunities for rationalization or even ethical challenges when it comes to human interaction. Some simple examples may be the selection of a job application or creditworthiness checks. There are other examples like face detection, where ethical mistakes occurred in the past. Finally, environmental aspects play a key role in today's factory operation. How can data-driven and autonomous systems be optimized in regard to environmental implications like temperature, dust, moisture, or any more that can affect curing time of glue, for example. Well, IoT devices. They are used a lot, and we use a lot of personal IoT devices, and they are also used in the industry. IoT devices are packed with a lot of sensors. Every data collection starts with sensors. Well, with a couple of sensors, okay, let's shorten this, with millions of sensors. Nowadays, IoT devices are often quite complex. Take modern cars, for example. They are equipped with a significant numbers of sensors. These cars are connected, sum up to large numbers of similar IoT devices, and in many world regions even transmit at a higher bandwidth. Computing power drops in costs, enabling a decent performance in edge computing, and thanks to hyperscalers, significant computer power can be accessed on demand. This enables us to scale in dimensions that we have never thought of and use big data analysis methods in a large number of use cases to understand underlying complexity and scaled physical systems beyond classical modeling. Okay, how does this work today? Here we look at a digital thread. Every use case on the right hand has its own digital thread. On the left hand, we have our data lake with the data of millions of real-life physical objects and billions of sensors. From our use case perspective, we have a digital thread from left to right, represented by the arrow, from data lake to ML pipeline to use case. Every use case is using its own machine learning model, represented in the middle by the nice brain. But this sums up to a large number of machine learning pipelines with no synergies between the individual pipelines. Every machine learning pipeline has to be maintained and retrained with every change to the physical object. With a growing number of use cases and physical objects, this leads to high maintenance costs. It's time to change the perspective on data understanding. That's the point where digital twins get interesting. A digital twin consists of three components. First, the physical entity, our object of interest that we try to understand. How does a physical entity behave in its real-world environment? How is the car used by its driver? Second, the data that is generated through sensors and real-time connectivity and stored on a secure cloud server. Third, the digital twin. The digital twin is a digital simulation of the real-life entity that reflects properties of interest at any point in time and extrapolates it into the future. The digital twin is not a simple collection of data, but represents the entity functionality and allows a digital simulation. Pointless data collection has nothing to do with a digital twin. On this slide, I try to explain how the change in perspective from a single digital thread per use case to a system of use cases is possible. The digital twin, shown in the middle, consists of a physical model and an artificial intelligence that go hand in hand. The beauty of a physical model is a fully transparent and human understandable collection of mathematical methods that describes relevant functionality of the modeled entity. The big advantage of this approach is that proven functionalities of the physical model can be used in related use cases. The use of a physical model offers the opportunity to keep and exploit valuable knowledge and intelligence property that has been built over years and decades within enterprises and describes them with mathematical methods. But when everything is described so nicely by a method, what is the rule of the artificial intelligence? Well, the AI engine analyzes the mathematical model and the available data to correct any deviation the mathematical results may show from the true results. When you will, artificial intelligence is used as a partner to help our scientists. We learn what the artificial intelligence has learned and use it for continuous improvement. With this step, the change in perspective towards a system of use cases is complete. The change from machine learning pipelines to individual physical entities opens even more possibilities. Let's stick to our car example. I think this is understandable for everybody. We can exploit as many big data methods as many individual cars exist. Every car has its own individual digital twin in the cloud. Every single digital twin does its own artificial intelligence-based learning. The learning affects the mathematical model and helps to improve the algorithm that represents all areas of interest that we have in our car. Our car learns when we leave for work and can precondition the temperature or heat the battery for hypercharging. If there are differences in behavior when it's sunny or rainy, on a sunny day, our driver maybe is using his e-bike. So no preconditioning of the car is necessary, and we can save the battery's energy. There might be learnings of global interest that can improve all digital twins, and there might be learnings of local interest that only affects my own digital twin. Less mature algorithms within a digital twin can easily be updated by a slightly more mature algorithm that was learned and developed within another similar digital twin. Maybe the driver is using his car in warmer regions and needs less preheating. How does this affect my battery lifetime? With other words, the machine learns from machines. This opens up the opportunity of dramatical fast developments. Other real-life physical objects can be added to the physical system and preconditioned by using existing mathematical models, and hereby keep and exploit valuable knowledge and intelligence property that has been gained during earlier development. But instead of a self-generating artificial intelligence neuronal network that often are a black box for the human mind, it remains explainable, extendable, and preconditionable. Now our IoT device from a couple of slides before has become a digital twin, much more powerful with real smart analytics, whose detailed analysis goes far beyond regular data reporting. By being still explainable, the causality of the data is extracted and underlying mechanisms are understood. The digital twin can now also be used for detailed planning in smart production, smart logistics, smart cities, and other use case scenarios. The explainability is a great advantage for everybody who is responsible for a whole system of autonomous entities like a production plant. The potential of prediction is huge, not ending with individual physical objects, but entire fleets. Apropos fleets, I will end my short excursion into the world of exponential growth with a more down-to-earth real-life challenge. The digital battery twins. But as every disruption, it starts small. So let's see how digital twins can help car manufacturers to understand the aging process of lithium-ion batteries better. And what can this good for? In fact, we are using electrical motors quite a while, even longer than combustion engines. So the big thing was a lithium-ion battery. More precise, the lithium cobalt dioxide cathode that was discovered in 1980 by a research group led by John Big-Data.AI at the University of Oxford. John Big-Data.AI, besides Stanley Whittingham and Akira Hoshino, earned the honor of Nobel Prize for Chemistry in 2019 for the work on lithium-ion batteries. Sometimes disruption takes a while. Now, here's the question. How can we attack technology challenges in battery operations? Obviously, the technological disruption is still underway. We have to be fast. Dating back to the 80s of the last century, it's still an entirely new technology to the automotive industry. We have no prior experience and now established implementation and operation approach. How can digital twins be used to tackle this? The fleet of electric vehicles containing lithium-ion batteries is growing fast. There are already predictions out there that we will see a 50% growth ratio in sales per year over the next 5 years. No wonder everybody wants to know as much as precise as possible about the aging process of lithium-ion batteries in real life. Modern cars are already connected and are collecting a lot of data continuously. Voltage, temperature, stage of charge, just to mention the obvious information. On the cloud server, every electric vehicle has its own digital twin. We can see and analyze every single battery across the whole fleet of electric vehicles. But data collection and data analysis is not the same as data understanding. As a starting point, the mathematical model that is used in our digital twin is derived from battery development and describes relevant functionality of the modeled entity. And then the digital twin is fast forward enhanced by the artificial intelligence, also learning from each other. The fleet operator, together with the engineers from the battery development, enables the cross-loop development and new batteries management, battery maintenance, and maybe even battery generations. The car improves over time, and new business models for the automotive industry can be calculated with higher accuracy. Many new use cases can be answered beyond battery management and predictive maintenance. We can realize warranty, contract management for used batteries, manage a second life in domestic home storage, or in big scale as grid-connected energy storage for network services, and many more. The disruption through digital twins is at the very first beginning. We have fascinating opportunities ahead. The integration of AI, big data, and IoT will get even deeper. Digital simulation based on real-life data will be used on every level with a common toolbox of algorithms. Informed decision-making via modeled scenarios will reduce business risks. Research and development, production and operation will work together in a closed loop, and many more to come. Many thanks for your attention. And as I always say, man's first step towards virtualization dates back to the development of script. However, opportunities have never been as stunning as today. Goodbye and have a nice afternoon.
Christian, thank you very much for this exciting presentation. Unfortunately, the time is over, but dear attendees, feel free to contact Christian on Swapcard.